Okay, so I know I've been gone for quite a bit of time, but today I'm going to finish off the series on heaps by showing you guys how we can create priority queues using heaps. Now, if you guys aren't sure what a priority queue is, I'd recommend that you check out my previous video on the topic. But the general idea of a priority queue is that it's like a normal queue, but we remove elements based upon which element has the highest or lowest priority, and we decide that when we're setting up the queue. And this property of dequeuing elements based upon the priority level is very useful for certain applications. For example, if you're doing multi-threading, you can make circular buffers with that, which is an advanced topic, but it's also used for other algorithms like Dijkstra's and A star. So I want to show you guys how we can set this data structure up using heaps, because there's certain properties about heaps which allows us to create this data structure using them in a very efficient way. So let's say I have an array of elements like this. So I've got 7 elements here. Actually, no, it's 8. So we've got 8 elements here, and I want to store them as a priority queue. And I can see that each of these numbers just represent a priority level. So you can think about these numbers just being a number to represent, let's say, some element that we want to store in the queue. For example, maybe position if we're doing some pathfinding algorithm, or maybe some task if we're doing some circular buffer for a multi-threading environment. So how would I turn this array of elements into a priority queue? Well, the first thing is I will turn this array into a min heap, and then I will construct a min heap, and the way I will do it is such that I will construct it one element at a time. What that means is I'm going to start off with an empty heap, then add one element at a time, and as I add each element to the top of the min heap, I'll use a top-down approach to bubble it down to the correct level so that we maintain this min heap property. Now the nice thing is we can just keep on repeating this element for each new element we add, and we always have this min heap property. Now the thing is, whenever we have a min heap, if I was to remove the top element of the min heap and then restructure the whole element again so that it maintains the min heap property, I have a priority queue of sorts, right? Because if you think about it, the first element of the root of a min heap is always the element which is going to have the lowest priority, right? Now, if I remove that element and then I reconstruct a min heap with the elements I've left, the element at the root again now is going to be the element with the lowest priority. So by doing that and popping off the top or popping the root of this min heap up every single time, I have a priority queue, because if I just keep on removing the root node, I get the lowest priority, and then I get the new lowest priority whenever I restructure the min heap. Now if I want to create a priority queue where the element which I dequeue first is the highest priority, right? So in this example, we are creating a priority queue where we dequeue based upon the lowest priority. Before I do it for the highest priority, we can just turn this min heap into a max heap and use the same top-down approach, which I'll show you guys, to reconstruct the max heap. So if that didn't make any sense to you, that's fine. I'll show you guys how this algorithm and this whole process works step by step. So I'm going to first have this empty array, which is going to represent my heap. And let's say I add the element 1 in, because this is the first element I enqueue into this heap. So 1 is going to be the root of this whole tree. I mean this whole heap, and it has no children so far, so we can just leave it as it is. Let's say I add 15. What you notice is I always add at the start of this array. So don't add towards the end, I add at the start. So now if I reconstruct this tree, 15 will be the new root node, and 1, which is going to be its left subchild. Now what I'm going to do now is I'm going to make sure I heapify this heap again, right? So I'll look at the root node 15, and in this case I want it to be a min heap because I want to dequeue based upon the lowest priority, and I'll explain what that means in a minute. But if I look at 15 and I compare it to the left subchild 1 is less than 15, so I just swap those two around, and now we maintain the min heap property. Let's say I add 5 now, so now 5 is the root node, and 1 is going to be the left subchild, and 15 will be the right subchild. Now if I look at this, once again, 1 is going to be smaller than 5, so I'm just going to swap those two, and 1 is smaller than 15, so we just keep that there. Let's say I add another element, for example, I add 12 to this priority queue. Well then, 12 will be the root node, 1 and 5 will be the left and right subchilds respectively, and then 15 will be the left subchild of 1, right? So right there's 15. So here I'm going to bubble down 12, and I'll show you guys what that means. So if I look at 12 right now at the root, I can see that out of the left right subchilds, 1 is the smallest, so I will swap 1 and 12. Now if I look at 12's new position as the root node of 15, I know that 12 is smaller than 15, so it's fine there, so I can just leave that there. If, let's say, if I had some number which is smaller than 15, so I had 7 down there as the left subchild of 12, I'd have to swap those two again, so I'll bubble the element down the heap until it finally gets to the correct position. Now let's say I want to remove an element from this priority queue. Well, actually, let's add one more element just in case. I add 3. So 3 right there is a new root node, 1 and 12 left and right subchilds, and I'll add 15 as the right subchild of 1. So if you guys aren't understanding how I'm constructing this tree, you can think of 3 as the root node, and then 1 and 12, so 2 times this number is going to be giving me the left subchild, and add 1, I get 12. So 3, 1, 12, this is the first binary tree. And then the left and right subchild of 1 will be 5 and 15. If I have 2 more elements here, so let's add 6 and 7, those will be the left and right subchild of 12. And then as we build up the tree, it works like that. So first I'll swap 1 and 3 because 1 is the smallest in that sub heap. Then if I look at this other sub tree right here, of 3, 5 and 15, 3 is the smallest, so we can just keep it there. Now what happens if I remove an element from the top of the min heap, right? So how can I dequeue? So right now we have a min heap, but if I want to make it behave like a priority queue and I want to have the dequeue operation work, how can I do that? Well, we just take the root of this whole min heap out from the heap. So I'll take away 1, and as you guys can see, 1 is actually the element with the lowest priority in this whole tree, right? Because that's the min heap property. The root's always the smallest element. I mean, it's the smallest number. So if I remove 1 from here and I redraw the tree, this is how it looks like. Now I have to make sure that the min heap property is satisfied. So look at the current root node of this entire heap, which is 3. And 3 is smaller than 5 and 12, so we can just leave it there, right? We still have the min heap property. If I now want to dequeue again, I remove 3, the first element, and the tree now looks like this. So I have 12, 5, and 15. Now 12 is a new root node, and if I compare it to 5 and 15, I can see that 5 is smaller than 12. So I just swap 5 and 12, and we have another min heap. And this is basically just how we construct the priority queue. We enqueue it using the top-down approach, which basically means I add one element at a time, and then I bubble the element down into its correct position in the min heap, such that it satisfies the min heap property. And if I want to dequeue from this priority queue, what I do is just remove the root node of the min heap, and then I just heapify the whole tree. I heapify the root node, and that will allow me to make sure that the whole tree is still a min heap. So I'll show you. Okay, so here I've got the code from the last tutorial about how we can use the bottom-up approach. I'm just going to remove this stuff right here, and I'm going to create a new heap array, and this is going to have 20 elements, right? And then I'm going to iterate over this array, and then I'm just going to set each of these elements to int max, and then I also have an index which is to us current index in the heap. So what int max is in this case is going to be the maximum value of a 4-byte integer. Now the reason it's a 4-byte integer is by default ints in C, they're not guaranteed, but they're usually just 4 bytes. So that's going to be 2 to the power of 32, right? That's going to give us, so 2 to the power of 32. This is the maximum integer size, or we have to do divided by 2. So if you guys don't know what's happening here, this is a signed integer, right? So a signed integer in C means that it can store negative and positive numbers. So half of the memory that we have to store this 4-byte integer is going to be for negative numbers, and the other half's for positive numbers. So if you think about it, the highest value I can store, or the highest number I can store inside this 4-byte integer, if you think about it, each byte is 8 bits, and if I have 4 bytes, that's 8 times 4, 32 bits, right? So 2 to the power of 32 bits, because each bit can be 0, 0, 1. So 2 to the power of 32 will tell me the highest number I can store, and then if I divide this by 2, I get the positive end of that. Remember, because half of that range is for negative numbers, and half of it's for positive numbers. So if I want to get the highest positive number it can be, I just divide it by 2. And int max is just a useful macro given to us by the C runtime library, which just stores the maximum positive number that a 4-byte integer can store. So the reason I'm setting this to a 4-byte integer, you'll see a bit later, but we need to make sure that it's a maximum integer, so when we start adding things into the array, the comparisons will work properly. I mean, into the min heap. If that doesn't make sense, don't worry. Once I start writing the code for actually adding elements into this min heap and then removing them, you'll see why we need the int max here. And then I also have this int index equals 0, and this is just the index. We're just going to use this index to gradually to keep track of where we are in the array, or where we are in the heap, and if we're full or not. So the next thing we have to do is write a function for appending to this priority queue, right? So how are we going to create this priority queue? So I'm going to create a function right here, and I'm going to call it, let's see, it's going to return a boolean. I'm going to call it heapify top down. It's going to pass in a heap, an index, a count, and then the new element. Right. So what does this mean? Well, you can actually just call this, let's say, if you want to call this, you can just call it priority queue. Let's call it priority queue NQ. So I'm just calling this. This is what's actually doing, right? This is the NQ operation for a priority queue. But I'm just calling it heapify top down because this is the algorithm which we're going to use to add this new element into the heap, such that from the outside we're using the interface of a priority queue, but in the inside it's represented as a min heap, right? So I'm just going to use this function to define the NQ operation into the heap. Now I'm passing in the heap as a pointer. I'm also passing in the index as a pointer because I need to modify it. I pass in a count, which is a maximum size of the array, then also pass in the new element I want to add. Now, currently I'm storing the new element as an integer, but let's say I'm trying to store, for example, if I'm doing a pathfinding algorithm and I'm using this as a priority queue, I can say that this is going to be a, let's say we can say it's going to be a struct which has a position, and it's also going to have a priority, and then in here, instead of just treating new element as an integer, we just extract that priority level and then we store it based upon that. So what I'm trying to say is, let's say we have position, actually, right. So let's say this is going to be a position in some pathfinding algorithm. So instead of passing in this new element here, which we're going to store in the queue, I'm going to pass in a position array, and then I pass in a position, right? And then when I'm actually adding it into the array, I will sort it based upon the new elements. Instead of doing something like when I'm heapifying, whenever I'm adding this into the min heap, I will sort it based upon the new elements priority level, right? So I'll do something like this. So then I will sort it into the correct position of the min heap based upon this priority level. But just for this simple demonstration, I'm not going to do that. I'm just going to use integers directly. So I'm going to say int right here. So the first thing you have to do is check if the heap's full, right? So if the value of the index plus 1, so we're trying to add a new element into this heap, if that's greater than the count, then it means that we can't store this element anymore, because then it's going to overflow the buffer. So it's going to return false, and this is why I'm returning a boolean. It's just to tell the user, have we successfully added this element into this priority queue or not. So in this case, if it's going to overflow the heap, so the heap's full, then we can't add any more elements to it, which is going to return false. Otherwise, we can move on to the process of actually writing the algorithm for the top-down approach. So I'm going to get the element at the top of the heap, right? I'm going to call this int lm, and then what I'm going to do is I'm going to move everything in the heap one to the left, right? One to the right. Okay, size of int times by the index minus 1. Now you may be asking, okay, actually no, this is incorrect. Sorry, that didn't make sense. So move everything to the right, so I get this thing. Right, so what does this line right here do? So let's say I've got a array, so I have 1, 2, 3, and then I've got a couple of empty spaces right here, right? So let's say we've got an array having 5 elements. What this is going to do is it's going to take everything from the start of the array and shift it 1 to the right. So now this will be 1, this will be 2, and this will be 3, right? Now if you look at this, I still have 1 as this number, so we're going to store this new element at the top of this array. So I'm going to say heap at 0 is equal to new element, right? And now that I've done that, I can just increment the index, right? So I'm just going to increment the index quickly, because now we've added an element. So this new element, let's say this new element is equal to 5. Now 5 is stored at the start, and we shifted all the other elements which were there before we added this element to the right by 1. So now that we've done that, we can just run this heapify function we wrote before in the last tutorial. So right here we've got this heapify function. So I'll just take this thing right here, and we'll just fill it out. So I'm going to pass in our heap, I'm going to pass in my index, I'm going to pass in my count, and then bool max or min, remember. So if you go back here, max or min. So if you have true, it's going to turn into a max heap. So right here, if max or min is true, then it's going to construct a max heap. If it's false, we're going to construct a min heap. So if we want to dequeue the element with the highest priority level, then we want to use a max heap, so we set max or min to true. If we want to do the opposite, so we want to have a priority queue where we dequeue the element with the lowest priority, then we're going to turn, we want to construct a min heap, so we set this to false. So since in the tutorial or the PowerPoint presentation I used a min heap as an example, I'm going to use a min heap here as well. So just pass in false, and once we've done that, we just pass in true. We just return true because we just successfully added this element into the heap. So if I just compile the code quickly to see if it works. Okay. Oh, okay, I have to dereference index because index is actually a pointer, right? And I think, yeah, that should be it. Actually, no, this is incorrect. I should do 1. So the reason we're not passing an index here is because when we specify the index for heapify, we're telling it the index to start bubbling down with the elements. So if you remember back in the PowerPoint presentation, I always started at the top, at the root node of the heap, and then I bubbled it down if I needed to satisfy the min heap property, and then I recursively kept on doing that. So we're going to do the same thing here. We're going to start off with the root node, and since we're starting to count the indexes from 1 here, I'm going to pass in 1 as the node we're going to heapify. The next thing we need is a function to dequeue from this priority queue. So say something like priority queue dequeue, right? I just pass in my heap, I pass in my index, and then pass in the count. Once again, so I'm going to check if the priority queue is empty this time. So if I dequeue index and I find that it's less than or equal to 0, it probably never will be less than 0. But let's say we've got some sort of bug or something happens and the number ends up being negative, we can just check right here. So if it's less than or equal to 0, we just return -1 as an error, right? And then I'm going to get the element at the root node, and this is the element we're going to return, by the way, right? So we always return from the root node. We're just going to take this node out of the heap, right? So if you take this array right here, if we're dequeuing, what I'm going to do is I'm just going to remove this root node right here. So I'm going to turn this into 1, and then this will be 2 and 3, and then I just start heapifying from the root node again to make sure it's a min heap. So now that I've taken out the root And now that I've got the value of the root node, I can do a mem move. So say everything from the right. So we've got the root node, which is at the start of this array, and then the rest of the elements in the heap are on the right. All these elements, one to the right from the root node, just shift them left. So now that, so what we'll basically just do is going to overwrite the min heap. It's going to overwrite the root node rather. So if I just do this, it's a size of integer times by the index minus 1. We're minusing 1 to remove to ignore the root node. And then I can just do a minus of the index, right? And then now that we've done this, we can just heapify the whole tree again. So I can just, for this thing, I can just use a bottom-up approach as well. That would also work. So instead of doing something like this, we can just do a heapify bottom-up. I pass in my heap, I pass in the count, then I pass in false because I'm trying to create a mid heap. Then I just return the element I was trying to dequeue. So let's test this out, right? So if I compile the code, okay, it compiles. So let's add some elements into this min heap. So I can say heap. Let me just quickly get the signature of this function. Let's see, heap, and then we pass in the index. We pass in the count, which is going to be array count of heap. This is a macro which calculates the size of the array, which will be 20. Then let's say pass in 10 first. Let's throw in a bunch of elements, right? So say 10, 2, 5, 30, 55, 1. Let's also pass in 3, right? So then if I just do all of this, and then after that I just print the array. So I've got the print array function we wrote before, right? So let's pass in the heap, then I pass in the index, or the count, so that's the index. Right, so now this is how we're storing the heap. So as you can see, we actually do have a min heap. Since 1 is the root, and then 3 and 5, 2, 10, 15, it stored it all correctly, so it's stored as a mid heap. So let's see if our dequeue function works properly. So let's say I want to dequeue an element, so I can do int element, let's say element returned is equal to priority queue dequeue, right? Then I pass in my heap, I pass in the index, the pointer to it, then I pass in the array count of the heap. Then let's see if I printf, oopsie, element returned, and then I print out the array heap index, right? And then I just do this a few times to see how it works, right? Okay, I'm gonna add some new lines to make it easier to read. Okay, so as you can see, this is the original heap, right? So if when I remove the first element, which is gonna be 1, so this is correct. This is the lowest priority in this whole. So out of all the elements I passed in, so I passed in 10, 25, 55, 1, and 3. 1 is the smallest, so it returned 1 first, and this is the new heap it can construct it afterwards. Then it returned 3, which is the second smallest, right? Then it returned 5, which is the third smallest, right here. Then it returned 10, and then if you keep on going with it, right, so if it returns 20, then returns 55, so then after that returns -1. So as you can see, we basically just created a heap, which is we've created a priority queue using a min heap. And as you can see, once we've basically done that, the array is empty, so then we start returning -1. So that's basically it. That's how we can construct a priority queue using a min heap. Now obviously, as I said before, you probably won't be passing in integers right here. So as you can see, you probably won't be passing in integers. You're probably doing something like, let's see. Let's use the example we had before, where this priority struct, or not priority, position, and then we have this position struct, int priority int x int y. Or actually, another way we can do this is, let's say you want to use this for multiple different structures, so we can do something like so we can do something like type def we can pass in a priority, and then we're going to have a union of different types it can be. So we have like this. Okay, so what I'm trying to do right here is show you guys what I mean. So it could be a position. One second, I'm just going to quickly add the code right here that explains what's happening. So right here, let's say we want to store multiple different types, right? So we want to have, let's say we want to store a position, we want to store some three-dimensional vector, we want to store some random piece of data, right? So we can do right here, so we're going to store these different types in this element. So we can create separate structs for each one, and then create separate functions for each of these different types. So for each type, you have to create a separate function for enqueuing onto priority queue and then dequeuing, right? Or what we can do is this other trick that's sort of online. So we can create this priority queue element struct, and inside of we're going to have the priority, which we're going to organize the elements based upon. And then we're going to have this enum called priority queue element type right here. And then we're going to have this union, which contains the different types you can have. So we can have a position, we can have a vector 3, we can have some random data, or whatever else you want. And then inside of this actual array, we can add some custom logic if we want to handle specific cases. Like if it's a position, we know how many bytes it is, or if it's a vector 3 or so some random data. So we can distinguish what type is being stored based upon this enum, and then we can store the different types using this union. So this is a cool technique you guys can use to store different types inside the priority queue without having to just create separate functions for each and every single type. Or if you don't want to do that, you can just do the old-fashioned way, which is, have a struct. Let's say, I don't know, have a priority queue pos position. Be like int priority int x and then int y, right? And then I would have to create each of these structs for each one of them. So let's say that's priority queue, then I have to have one for priority queue vector 3, and then one more for right? So if I can either use this method, which is kind of nice, where I can just store all these different types in a union, and then I can distinguish which type it is based upon the value in this enum. Or if I wanted to do and this way I can just have one set of functions for both of these, right? And I have to change the code obviously to adjust for it, but you get the idea. Or if I don't use this approach, I have to do the other approach, which is I create a separate structure for each type I want to store inside of this queue, and then I'd have to create separate functions to handle each one of these, which is a lot more code, a lot more verbose. It would be nice if we had some kind of generic system such as templates in C, but we don't, because it's C, it's not C++. So this is, in my opinion, this is the best thing we can do with what we have. So we just use a union, and then we have this enum which we use to find out what type it is. So that's pretty much it for the tutorial. I hope you guys enjoyed it, and if you have any questions, I'd be happy to answer them in the description below. Also, if you haven't checked out some of my previous videos, like my series on arenas, allocators, then I highly recommend that you check it out. And thank you for watching. Bye.